10.5 in the last subchapter from this chapter, it talks about recursive rules for sequences, and we talked about how up until now we had explicit rules. This is just an example, and really what it tells you that the nth term or that term of that sequence depends on how many terms are in the sequence. So an was directly dependable of how many of n terms were in that sequence. The recursive rule, your an term depends on the previous one or previous more terms. For example, one of the examples would be an equals n times n minus 1. So I would need to know the one before, the one I'm looking for, in order to get to where I need to be. It sounds confusing. It was confusing in class too, but we're going to work it and see. On number 1, it says, write the first 4 terms. You know a0 is 1, and you know the recursive rule is an equals n times an minus 1. So I already have a0 I'm looking for. a1, a2, a3, a4, and a5. These are the terms I'm looking for, right? It's the first terms, skipping that a0. That's where I started. That's where I'm going. So let's go ahead and do this. a1 equals n, which is 1. Notice the same letter, times n minus 1 minus 0. I'm looking for a0. 1 times 1, which is 1. a2 is going to be how many? What is n now? 2 times 2 minus 1. I'm looking for what's the value of a1? 1, which is 2. a3 is going to be 3, because this is a number, times what was the value of the term ahead of me? 2, which is 6. Let's move on to a4. This is 4 times the value of the number in front of this one, 6, 24, and then this becomes 5 times the value of the number in front of this one, 24, 120, right? So if you notice, my next number is going to be whatever place it has in line times the value of the number previous to him. Here's the second example. a1 is 1, a2 is 1, and we need the first 5 terms, which is great because we just need a3, a4, and a5. And they tell me the rule. Whatever term I'm looking for is the sum of the 2 previous terms in front of them. So for a3, I need to add a1 and a2, right? This becomes 1 plus 1 equals 2. For a4, I need to add a2 plus a3, right? 4 minus 2 would be 2, which means 1 plus 2 is 3. For a5, I'm adding a3 plus a4, which is 3 plus 2, which is 5, right? 2, 3, 5, 1, 1, that's our series. So it's always depending on the rule that you have ahead of you in order to be able to work these. And these recursing rules can get confusing, but if we work them slowly, we will figure them out. We're going to move on example 2 in just a second, but my computer is dying. I need to bring the course. I'm going to pause. Okay, computer saved and plugged in. Let's go ahead and work on example 2 that talks about write the indicated rule for the arithmetic sequence with a1 is 4 and these 3. Remember arithmetic sequences and series from, I think it was 11.2? Here's where we are. That formula you already have down. This is the explicit rule. So the explicit rule will be very easy because you have a 4 and you have a 3. You have a1 and d, you're good to go. an is 4 plus n minus 1 times 3, or 4 plus 3n minus 3, or 1 plus 3n. And I got this down as an explicit. The explicit one we had the formula, we worked it out. When it comes to the recursive, you need to think of anything that means arithmetic. That means we have a difference, which means if my first term is 4, my next one will be 7. My next one will be 10. Why? Because we keep adding the difference, right? My next one will be 13, which means I can write the recursive rule saying this term will always be the previous term plus the difference every single time. This one will be the term in front of it plus the difference. This one will be the term in front of it plus the difference. So my rule for this case would be an equals an minus 1, the previous term, plus whatever my difference is. So let's go ahead and replace what we know. In this case, I can go AN, and I'm going to make sure that I know what I'm doing in here. AN equals AN minus 1 plus 3, right? And I have gotten my recursive rule. All I had to do in this case was a lot easier. All I had to do is plug the difference because I don't know the rest of the terms unless I start working them out. But when you have explicit, you already have a rule. You just have to go back to that rule and get that. When it comes to recursive, you're going to have to think it through and think, okay, if this is arithmetic, my next term is always be the previous plus my difference, and that's going to be the rule, okay? So I hope this makes sense and it brings back memories from class. Example 3, we're now moving into geometric sequences, right? And it tells you you get a geometric sequence, first term is 3, your ratio is 0.1, and it says write the explicit rule and write the recursive rule. Again, explicit, we already had the rule. 11.3 gave us the rule, so this just becomes AN equals my first term, 3 times my ratio, 0.1 to the n minus 1. I'm done. This is my explicit. The recursive, you're going to have to think it through it, okay? So if this is my first term and that's my ratio, here's going to work. My first term is 3. My next term is going to be 0.3. My next one, I actually need to use a calculator to make sure that I'm not doing this wrong. 0.3 times, now, 0.1 is going to be 0.03 and so forth, right? So if I have to think about what will this be, it's going to be the previous term times my ratio. This one is going to be this one times my ratio and so forth. So my recursive rule for this one would be AN equals my ratio times the term ahead of me. And why is that? Because in order to find that ratio, we always go this divided by this, gives me the ratio. So in this case, once we got the formula down, I can go AN equals my ratio, 0.1 times I don't need the parentheses here, I'm sorry, n minus 1, and this is my recursive. How do I know the difference in between them again? The explicit, your A of n, only depends on your n, right? How many terms you have. In the recursive, if we're using AN, and the previous term, the terms right in front of it, that makes it the recursive, okay? Now, let's look at the last part of this, which is example 3 from working class. And it says, write the recursive rule for the sequences. 1, 2, 2, 4, 8, what's after 8? 32. We need to come up with a recursive rule, which means we're going to have to write this term in terms of this term, this one in terms of something, this one, and so forth. So I'm looking at this and I'm thinking, I don't see any difference in here, but I'm looking at this 2 and I'm thinking this 2 is this times this. 1 times 2 gives me this, correct? 2 times 2 gives me this one. 2 times 4 gives me this one, and so forth. If you look at this, these 2 times together is this one is this one, these 2 times together is that one, which means I can write a recursive number and say A, let's just write it normally. 1, 2, 3, 4, 5, 6. A6 would be A4 times A5, right? 4 times 8 is 32, which means AN is going to be AN minus 2 times AN minus 1. While they're tricky, and you're going to have to spend some time looking into it and figuring out rules, eventually your brain will catch up with it. There's always going to be a connection to where you can go. Well, this is this times 3, or this is this times this, or this is this times, and so forth like that, to where you can find a difference. Now, keep in mind that in this one, it's just called a sequence. If you look at them, it's not arithmetic and it's not geometric. It's just a sequence, but it still has a recursive rule. And I'm going to let you take a second, pause this, and read problem 5 so we can work the word problem, and then we're done. Okay, let's work out this problem. And this is about a pond that has, at the beginning of the year, it has 5,200 fish, and it says that each year the population of the fish goes down 30%, and at the end of the year they get 400 new fish in the pond. So the way we wrote this rule was fish at the start of any year, we called it nth year, is going to be 70% or 0.7, because we're losing 0.3 of what we had the previous year, plus the new fish that were added. If I would be to write this as a recursive formula, it would be an, right, the nth year, would be 0.7 times the previous year and minus 1, plus I get 400 extra fish. And this is just my recursive rule. We wrote the recursive rule. My current year fully depends on the year past up. The next thing in the same thing, he said, how many fish are in the lake at the beginning of the 5th year? And this is the fun experiment we did with the calculator. So I want to remind you how to do it. I'm going to clear it all out. And we said we're going to put in, what did we start with? 5,200, right? Then we're going to hit enter. And then we're going to take that number by not pushing anything else but timing it, which is going to give me that answer which I'm looking for, times 0.7. We're just going to write a recursive rule, and then plus 400. And that's going to give me the population at the 2nd year, right? And then we said if we keep pushing enter one more time, I get the population the 3rd year. Let me put it in here. And then this is the 4th year. This is the 5th year. So about the 5th year, we're going to get 2,262 fish in the pond in the 5th year. About 2,262 fish, right? We did this really smartly by putting in initially the initial amount that we knew we started with, and then we're going to times that. So we just went and hit enter, times it by 0.7, which brought us to that answer. And every time that answer pops up, it just goes to the previous one. The reason we're doing this, once this stabilizes, this answer, oh, I can't get it to. Okay, more or less. You know what I'm talking about because I looked at it in class. Now, it says here in part B what happens after a while of time. So the way we did it in class, we're going to do it here. We're going to keep hitting enter. And then once you keep hitting enter, you're going to notice that you're getting very close to the same number. 1333.33 kind of goes down to very, very, very little. One by one, it goes down, but not much, right? So really, within time, we know that the population of fish in this lake will be close to 1,333 fish. It's going to stabilize and it's going to stay there. And so this was an easy word problem because we used the calculator for most of it. The most important part was the word part that we're going to use here to make sure we write the rule correctly. And that's it. This is the whole chapter 11. Happy homework and happy testing.